Okay, so just 2 more minutes because there's a continuous influx of students. And if I switch from this screen and start with the presentation, I'll have to again come back to the meet window and then accept students. So just 2 more minutes, guys, and then we'll start. So it is also requested to everyone that we'll have the session, this live session for Biomedical Nanotechnology BT-70 every Friday at every Friday at 6 p.m. So you all are requested to join at least 5 minutes in advance so that we can start the session on time and we do not have to wait for everyone to join. So it would be better for all of us because we'll be able to start early. So just 1 minute more and then we can start. Okay, I can do one thing. Maybe I can join from my phone and then accept the request from there. Okay, so yeah, there are different TA sessions. So that is basically designed for you to basically, a lot of times it might happen because some of you might be going to college or have some other work or like that. So there are different time slots that are available. So basically, it is suggested, it is encouraged that you attend all the TA sessions because all the live sessions will be dealing with different information, different sample questions. Just a second. Okay. So yes, so the answer to your question is yes, you can join all the TA sessions, but then it also depends on your availability and your interest that how you're finding the different live sessions because obviously the topics would be more or less same, but the teaching style, the content material, the sample questions that different uh, course members would be dealing will be different. So obviously it would be beneficial for you if you're interested. You can definitely join all the sessions. If because of some work or because you're engaged somewhere else, you miss one, you can attend the other one. I request all the students to please switch off uh, their mic. Okay. So yeah, my audio is visible. Uh, okay. Okay, so let's start. My audio is clear, my video is clear. Now yeah, the screen is visible to everyone. Okay, let's start. So starting with, let us begin with my introduction. My name is Anusha Srivastava. I am a Prime Minister's Research Fellow and I'm currently doing PhD at Indian Institute of Technology, Indore. And I'm currently in Department of Biosciences and Biomedical Engineering. I am also working on nanotechnology. Basically, I'm working on photothermal therapy. I hope a lot of you might have heard, or most of you may not be aware also what exactly is photothermal therapy. So I believe everybody knows about cancer, everybody knows chemotherapy. That is something that we often hear, you know. But photothermal therapy basically is, when we use light and there is a photothermal agent which basically absorbs light and there is killing of cancer cells. So that is photothermal therapy. Now, that is my introduction. But today's live session, that is the week one NPTEL live session, basically, basically, we'll deal with some sample questions, but the pattern that we'll follow will be a little different. Like these are the topics that you're seeing on the screen. Okay. So these are the topics that your course instructor has already covered. You have access to the videos, you have course content and everything. So in this particular live session, what we'll be doing is we'll be looking at the assignment questions that you have got that is already uploaded at the NPTEL website and what is the, how you can solve those questions. What is the approach basically towards solving those questions? So course content is available, everything is there, but apart from that, suppose there's a question and suppose you know the answer, but there's also a theory, there's an important concept, there's an important theoretical concept that is attached to that question. So we'll look at that. So the approach would be we'll look at the questions, and then based on that we'll also revisit the important topics, the important theoretical concepts based on which that question was framed. So let us start. So the very first question that was there in your week one assignment was, choose the appropriate characteristic of incidental nanoparticles. So I hope a lot of you might have already submitted your week one assignment, but if you haven't, you can just uh, go through, check the answers. So apart from this assignment questions, we'll also be discussing some other sample questions as well. So obviously the answer was, like for the incidental nanoparticles, the answer was composed of different elements and non-uniform size. Now, if you remember, it was also discussed in your class that what are the differences between, there are two types. One is incidental and the other one is engineered nanoparticles. Now, what is the difference? These are more variable in nature and these are more well defined in nature. So they have different sizes and shapes, as you can, as you can see, right? So they are also composed of different elements, their size differs, their shape differs. But engineered means they are more structured. You have specially crafted it, you have curated it by different methods. The method could be like, as you have also studied, like it could be by physical means, it could be by chemical means, it could be by biosynthesis of nanoparticles. So whenever you are engineering, you are creating nanoparticles, obviously that is because you are, that will be more structured, more organized. So let us have a look at the definition again. So what is the definition for engineered nanoparticles? It is intentionally designed, because why are you synthesizing nanoparticles? Why are you synthesizing different nanomaterials, nanoconstructs? Because you have an intended application in your mind, right? For different biomedical applications. Suppose you want to deliver a drug that, suppose chemotherapeutic drugs, we all know it causes systemic toxicity. It is highly toxic to the body. It is highly toxic not only to the cancer cells but also to the healthy cells. That is why there are a lot of side effects for chemotherapy, correct? So suppose you have uh, nanoparticles. Suppose you want to load a chemotherapeutic drug in that so that it increases the bioavailability of the drug and there is sustained release, and there are different, there could be different biomedical applications for that. So you are engineering nanoparticles. Maybe there's a nanoparticle, you are loading some drug in it, and then apart from that, you're also adding some kind of, you know, attaching targeting moieties here. So maybe these targeting moieties can go and target receptors present on the cancer cells, which will lead to better delivery of your drug at the target site. So the main, benefit of doing nanoparticle mediated delivery of any chemotherapeutic or any drug is that it increases the bioavailability. Then apart from that, it also, you can do the targeted delivery at a particular position, at a particular site, at the tumor site. But in chemotherapy, you're giving IV, so it is going through all of your body and causing all the harm. Okay. So what are the examples? Silver nanoparticles, gold nanoparticles. Sir has also shown in the NPTEL lectures like how these are synthesized, how you optimize the different conditions and different parameters. So what are the examples? Silver nanoparticles, gold nanoparticles, titanium dioxide, carbon nanotubes, quantum dots. Incidental nanoparticles, what are the characteristics of incidental nanoparticles? Unintentionally formed as byproducts of natural processes or human activities. There is no control over their size, shape, or surface chemistry, and they are highly variable. What are the examples? Suppose soot from vehicle exhaust, because the soot particles that would be there would be no uniformity, right? There would be different shapes, there would be different sizes, then welding fumes, volcanic ash, dust from mining, smoke from cooking, and different kind of, there are so many more examples. Now, these are some of the common, these are some of the common engineered nanoparticles that you would come across while going through this particular lecture series, Biomedical Nanotechnology. Nanosphere, like solid, or nanosphere solid gold, then nanosphere polymeric hydrogel. So there are different materials basically which can be used to engineer nanoparticles to make nanoparticles. Then nanorod, nanocapsules. Then these are, lipid-based nanoparticles. There are peptide-based, protein-based nanoparticles. So a lot of varieties are there. Then, interestingly, you would have also you would have also read about this virus-like nanoparticles. So, what exactly is virus-like nanoparticles? Basically, you are removing the viral genome which is responsible for causing infection, and the shell that is remaining, that is basically used as a delivery carrier. So, what you are doing in all those things, you are engineering that nanoparticles. That is why the term engineered is used. Correct? Moving forward, so in this lecture, apart from the usual content, the bookish content that is there, we'll also see how nanotechnology is, there in our lives, and a lot of times we kind of miss it. We don't even know that in our daily life it has occupied a place in our daily life, but a lot of applications we are completely unaware about. So this is just a timeline which is summarizing ancient civilizations where people produced and used nanomaterials, but at that time they were not aware of their nano size characteristics, so they did not know that those materials that they are using are actually nanomaterials. So, suppose look at this example. So, hair dye nanoparticles based. So, people were dyeing their hair, but they did not know that it actually, just they were nanoparticles. The molecules that were used for dyeing the hair were actually nano in size. Now, one interesting example is, I hope basically boys might not be aware, but girls would know there are different hair treatments that are available currently in the market. There is keratin, there is cysteine treatment, then there is Botox, smoothening, straightening. So, but there is also one new application that has, recently been introduced. So recently, when I went to a salon, so I was made aware about this one, which is nanoplastia. What exactly is nanoplastia? Nanoplastia is a nanotechnology based hair treatment designed to smooth, straighten, and repair hair by delivering active ingredients deep into the hair shaft. So, as we just studied, that if we are loading our bioactive molecules into the nanoparticle and then delivering it, its bioavailability increases, it can penetrate deeper. So, based on this concept, the people who are doing the cosmetics and the scientists have come together and incorporated this knowledge of nanotechnology for personal care and aesthetics. So, a cosmetic hair procedure using nanoparticles to carry keratin, amino acids, vitamins, and other nutrients. Basically, all those bioactive molecules and you know nutrients which will basically make your hair look shinier. It will make it hydrated, straight, and manageable. So, uh, this particular treatment is nothing but the application of nanotechnology. People were using it in earlier times for dyeing and all those things, but they were not aware. Now, moving forward, there were some classic examples as well, which one of which is this Lycurgus cup, which is a 4th century Roman cage cup made of a dichroic glass, meaning it changes color depending on the light source. So, see, we often see different colors, and that phenomena is basically observed because of the reason how light interacts with the material, whether it is reflected, whether it is transmitted, whether it is scattered. So, based on which phenomena is taking place, whether reflection is taking place, whether transmittance is taking place, whether scattering is taking place, you would see different colors. So, when this glass is lit from behind, it appears red because what you are seeing is the transmitted light, correct? Suppose this is the glass, you lit it from behind and you are at the front. So whatever light is coming, that is transmitted light, correct? So when light is transmitted through the cup backlit, the gold and silver nanoparticles causes a red hue. You will see a red color. But when you're standing in front and you're shining it from like from the front side, so in that case, what is happening? So suppose you are this here is the light source. You are also here, and light is going, interacting with the gold and silver nanoparticles and coming back to you. So that is reflected light, correct? So when light is reflected off the cup frontly, the nanoparticles scatter the light, resulting in a green color, correct? Now, another example is Egyptian blue. What is Egyptian blue? So it is world's first synthetic pigment and was extensively used in ancient Egypt for painting and other applications due to its vibrant blue color and durability. It's now recognized that the pigment's ability to absorb visible light and emit NIR radiation makes it a promising material for various modern technologies, including biomedical imaging and energy saving applications. So, what is happening with this Egyptian blue? So, it has a characteristic that when you will excite it with, you know, light in the visible region, we will excite with the visible light. It emits in the near infrared radiation. I hope you all would be aware about the electromagnetic spectrum. There is UV region, there is visible region, and there is near infrared region. So you are shining light in the visible region, but it is emitting in the near infrared region. So this particular property of Egyptian blue is basically used in, imaging. Basically, like suppose you want to image cells, you want you want to image cells. Like there are different experiments when you stain the cells with a particular dye and then you collect the images. So it is giving light in the near infrared region. Now, another one is this Damascus sabers, renowned for their strength and unique patterns. Surprisingly, contain carbon nanotubes and cementite. So this one, dates back to 1200 AC, this Damascus saber. But when scientists, delved into it, that uh, what is it composed of, they found that it contained carbon nanotubes and cementite nanowires, a form of nanotechnology according to research. Now, another question that was there in your assignment was this one. The question was, the assertion was energy savings window designed to stop thermal radiation escaping in winter and prevent the entry of infrared radiation from the sun entering the building. Okay, reason क्या है? The window glass is coated with thin film, 5 to 10 nanometer of vanadium oxide. So, in order to answer this question, you shall know what exactly vanadium dioxide is doing in this case. So, vanadium dioxide exhibits a thermochromic property. What does that mean? It means that at low temperatures, it is transparent. It is talking about, here it is written, it stops thermal radiation escaping in winter. So in winters, you obviously want there is, warm temperature inside. So at low temperatures, when there is cold outside, it is transparent to visible light, but blocks infrared radiation, keeps heat in during winters, and keeps heat out during summer. At high temperature, it changes phase and reflects infrared radiation. So this is the property of vanadium dioxide, and this characteristic that it shows, the term for that is it shows thermochromic property. Now, next question for your assignment was cowpea chlorotic mottle virus. So this is basically when you're using virus-like particles for, in nanotechnology. So obviously you guys would have already done the assignments, but let us understand, let us dwell a little more deeper what exactly is cowpea chlorotic mottle virus. So cowpea chlorotic mottle virus has distinct inner versus outer chemistries. So, whenever we are studying nanotechnology, whenever we are talking about nanoparticles, it is very essential it is very essential to understand their structure, their their basically their morphology, their structure, their surface chemistry. Why is it important? Their chemical nature is very important. Suppose you select a delivery vehicle, basically a nanoparticle, and you want to load a drug in it. Suppose that is the case. Suppose, let me just draw. Suppose you select a delivery carrier. Suppose you select a delivery carrier. Okay. Now, this delivery carrier that you have selected, suppose it is, okay, so I am making it with mouse, so just pardon me for the mess. Suppose it has hydrophobic. This nanoparticle, this delivery vehicle that you're using, so this is hydrophobic in nature. Okay. Now, if you are loading a drug in it, suppose you are loading a drug in it, okay, and if that drug is, so if that drug is hydrophilic, there would be difficulty loading that hydrophilic drug in a hydrophobic nanocarrier. So that is why when I said, when you're talking about nanotechnology, when we're talking about nanoparticles, it is very important to understand their surface chemistry. It is also very important to know their structure. What is the nature? Whether it is hydrophilic, whether it is hydrophobic, whether it is soluble in water-based solvents, whether it is, soluble in organic solvents. So all these things vary. But if you load a hydrophobic drug in a hydrophobic nanocarrier, it would be easy. Similarly, if you load a hydrophilic drug in a hydrophilic carrier, it would be more easy. So these are the considerations that we need to pay attention to. Now coming again to cow pea chlorotic mottle virus. What is happening here? The interior capsid surface is more positively charged than the exterior to bind the anionic RNA genome. Now, why this interior capsid surface is more positive than exterior? So that it can bind the anionic RNA genome. So basically ये आपको इसलिए पता होना चाहिए. Why do you need to know this? Because in order to solve these statement type of questions, you need to know. So obviously the answer was first in, okay, just a second. I'll just, if somebody is asking something, I'll just open the chat box maybe on my phone so that I can read it. Okay, so there are two questions. So let us first answer those questions. So the first question was, how do we know that this nanoplastia, that if we are using it, how is it ensuring that it is reaching to the core? So basically, what happens is whenever a product comes into the market, there's a lot of testing that has been done behind it. And suppose, uh, okay, so there is a skincare brand. I guess a lot of you might know that there is a skincare brand, Minimalist. Okay, so what Minimalist, if you'll open Amazon or Myntra or anywhere where it is available, you will swipe off the photos that are available. You will see there is a mention that it is has been clinically tested. It has been scientifically tested to, and where it has been shown, where it has been scientifically shown that it has, improved the outcomes. So similarly, when we talk about nanoplastia, obviously it would have been tested on different hair types on the response, correct? So it has been tested for different hairs, different kind of hairs. So it would have been scientifically tested that it has reduced the frizz, it has improved the smoothness. So whenever we are testing, suppose a new product, we usually compare it with the gold standard, correct? So suppose there is a smoothing treatment that is already available. You do it on one similar kind of hair type or patch. So there is a patch test basically. So you did it in a, one section of hair, and in the other section of hair, you suppose you do the nanoplastia. So obviously you would see the differences. So based on those different experiments, it depends which brand is following, what is the, path that they are following. But usually it is scientifically tested. That is why it is claimed that it has scientifically shown to improve the outcomes. So yeah, that is the answer to the first question. Now the second question is CCMV only known carrier or there are many? There are different kind of, see, this is only cowpea chlorotic mottle virus is only one type. There is tobacco mosaic virus. Once we remove the viral genome from it, then tobacco mosaic virus can also be used for the delivery of whichever agent you want to deliver. So it's not just CCMV. There are a lot of them available. Like there is cowpea mosaic virus, there is tobacco mosaic virus, a lot of them are available. So since this question was cowpea chlorotic mottle virus, so I am only discussing about this one here. I have also attached some other uh, examples as well based on the sample questions. So cowpea chlorotic mottle virus is a well-studied plant virus and a model system in viral nanotechnology. Okay, because of its simple and tunable chemistry. Now, यहाँ पे एक term आता है that we call tunable. What does tunable mean? Tunable means you are able to modify its characteristics. You are able to control its size. You are able to control its shape. You are able to modify its surface. So for this particular tunable term, we'll discuss in detail. I have attached images as well that will come up in the subsequent slides, where you'll just have the clear concept what exactly means that a particular nanoparticle can be tuned based on our application. Suppose we want 20 nanometer of nanoparticle. Suppose we want 60 nanometer of nanoparticle for a different application. So you can tune the size of nanoparticles by optimizing different parameters like you know concentration, temperature, and maybe changing solvent. A lot of things are available. So this one is clear. Now moving forward. Okay. No, actually, when you are, making the reason why this viral nanotechnology basically comes under biosynthesis of nanoparticles, and it is also considered a green chemistry approach, because when you are engineering virus for nanotechnology application, you are making sure that it has no infectious agent or infectious components that is still there. So you are processing it, you are engineering it to a delivery vehicle, I mean, into a delivery vehicle that will only deliver your particles, and then it will be just undergo biodegrade, like it will biodegrade and it will be eliminated from the body. So no, it will not cause infection. Now let us have a look at various structural comparison of some plant viruses which is used to build nanoscale materials. Okay, so plant viruses as a biotemplate, okay, for nanomaterial fabrication. So this is cowpea mosaic virus. This one is cowpea chlorotic mottle virus. So it differs. Okay, so some people are still joining. Just a second. So usually I'll obviously let you in, but it will be great if you guys can join at 6 p.m. But it's fine. So okay, so how does these vary? So it has icosahedral geometry, and it is made up of 120 units. This one is made up of 180 units. So this is brome mosaic virus. Then this one is quite commonly used. This tobacco mosaic virus. Okay, so it has see the nano features. It is 300 nanometers in length and 18 nanometers in this transfer section. So that is why, because of the size, because of their nano sizes, these plant virus have been proposed as a biotemplate for nanomaterial fabrication. And what are the applications in nanotechnology? Cargo encapsulation. Suppose you want to do gene delivery, you want to do DNA delivery, enzyme. Suppose you want to, encapsulate drugs in these viral virus-like nanoparticles. So the first application obviously is cargo encapsulation. Then exterior modification. What does that mean? Just now I told you, suppose you attach some kind of targeting moieties here. Okay, you attach some kind of targeting moieties here, and now these targeting moieties are such that it will go to a particular site and react to these receptors. Suppose this is, so what would happen? It will lead to a very targeted approach for the delivery of such drugs or molecules, whatever you are, loading in that. So you can do exterior modification. So that is, one feature. Then nanomaterial synthesis. So template for metal nanoparticles, semiconductors, and magnetic materials. Then drug and gene delivery. Okay, and then drug and gene delivery. Now moving forward. So, okay, now for this, I hope a lot of you who are active, you can do it in your mind as well. But you can also write the answers for these questions, and then I'll also show you the answers. What are the correct answers for that? So, I will just wait for 15 seconds and then I'll show the answers. Meanwhile, please try attempting these questions. Okay, I'll just set a timer for that. I'll set a timer. Usually, I encourage you to write the answers in the chat box, but because this is basically for your preparation, this is basically for your, you know, practice and to check how much you have understood. Okay, so the question, can we as an individual make these or developing is very costly? Okay, so it depends what kind of nanoparticles you are making. So suppose you are making simple metallic nanoparticles. Okay, you are making, suppose you're making gold nanoparticles. Okay, so for that, what do you need? You need fluoroauric acid, you need sodium citrate, you need heating block or with a stirrer, and then you can make it. So making that, it depends on the raw materials that are needed for that, and not only the raw materials, the instrumentation that is needed, the technical, you know, the, what are the technicalities involved with the synthesis, because the synthesis process differs. Now, suppose you want to make copper nanoparticles. Okay, so there could be two different routes for that. One is you're doing a chemical synthesis. So for chemical synthesis, what you need basically a copper precursor. So basically you need a copper precursor, which could be copper sulfate, it could be copper nitrate, and then you are using a reducing agent basically, and then you are making copper nanoparticles. Another approach is you can have plant extracts. There are a lot of plant extracts which have different bioactive molecules like polyphenols, alkaloids, and a lot of different components which are there in the plant extracts. And these plant extracts possess like great potential to act as reducing agent. So in first case, when you are doing the chemical synthesis, you are using suppose copper sulfate with a reducing agent. In second case, you are using copper sulfate with plant extract, which will help in reducing that that copper sulfate, and there will be formation of copper nanoparticles. So how you are synthesizing nanoparticles, then which what kind of nanoparticles you are synthesizing. Then again, suppose if we talk about cancer therapy, if we talk about treating tumors basically. So if let's say chemotherapy is, if you compare it with immunotherapy in which you're using all those antibody mediated, or a lot of approaches are there, but chemotherapy is comparatively cheap. That is why it is being used, but it is not safe. It is very harmful. It causes toxicity, and a lot of times it happens that in if the person's body is not, the person is not very strong, it is, the immune system is compromised, even with the first dose of chemo is administered to that patient, and that person collapses, like not because of the cancer but because of the secondary causes, because of the toxicity that these chemotherapeutics bring. That is why there is a continuous, you know uh, effort to bring in more safer technologies. You would have come across a term that is green chemistry mediated synthesis of nanoparticles. Like, you're using green chemistry, you're not using any harsh chemicals, you're not using any toxins and all those things for synthesizing nanoparticle. Now, one of the reasons, yes, doxorubicin is approved, but again, two major problems associated with doxorubicin is that first of all, it causes systemic toxicity. You would experience appetite loss, nausea, hair loss, and then it causes, and it is cytotoxic. It will not only cause toxicity towards cancer cells, it will also, cause toxicity towards your, no, healthy normal cells. Obviously, the percentage would be different, like how is it affecting? But again, and the other problem is if you're using it so much, after a certain time, it will start developing, the cancer cells will start developing resistance against doxorubicin. Correct. So that is the problem with chemotherapy nowadays. So there are certain drugs which have been actually FDA approved for the treatment, but again, the main problem that we are currently facing is that it is extremely toxic. And in addition to that, there is the problem of development of drug resistance towards that drug. So that is why different approaches are coming. This particularly the nanotechnology in which we are loading the drug and then delivering it at a particular, in a very targeted manner so that only cancer cells are destroyed. Now, and usually if you have like come across or listen from your relatives or like that, you would have you would know that chemotherapy is not always given alone. It is mostly, um, paired with different therapies that are available. Sometimes it is paired with radiation therapy to obviously enhance the efficiency of this of the therapy. Sometimes once the surgery is done, then cleaning of cancer cells, correct, dual therapy or that what is called combinational therapy. So there is, uh, suppose there is surgical removal, then, whatever cancer cells are remaining, it is cleared using chemotherapy or radiation therapy. And once it is done for the palliative care, what is palliative care? Palliative care means once your cancer, like surgically, it has been removed and it has been cleared, but for post-operative care or post-treatment care के लिए, you also use hormonal therapy. So there are obviously some medicines that are available that is used for hormonal therapy. So there is a combination of different therapies that is given to patients. Now I'm talking basically about in case of suppose breast cancer, which is quite common in females. So there is a combination of therapies, and what combination would be used actually depends on the molecular subtype and also what type of cancer is there and how deeply rooted it is, whether it is possible to do the surgical resection or not. So a lot of things are there. Okay. Can we as individuals try to develop a new drug using safe materials? Okay, see, drug discovery. Okay, now there is another important concept. You would have listened about drug repurposing, correct? And the most, I would say, one common example that we have recently seen was during the COVID-19 infection. The drug that was usually given to patient was actually intended for some different application, but we did drug repurposing in that case and started giving to COVID-19 affected patients. So yes, there is a continuous effort to bring in new drugs. Sometimes it is extracted from different plant materials. Sometimes it is like you are doing, yes, there is a lot of computational studies are also being done to check how a particular bioactive molecule present in some plant extract or present from some different source will interact with the cancer cells. So yes, uh, different drugs are being discovered, but most recently a new approach is the drug repurposing. Like suppose a drug that is meant to treat some other disease is also tested to see if it can help cure some other disease in which its intended application is not known earlier. So that is the approach. Now coming to the answers for these questions. So the first question was, what makes virus attractive as nanotechnology tools? So the different options were, they are electrically neutral, they have uniform size and shape at the nanoscale, they can replicate in living cells. Obviously, this is like there, but यहाँ पे what you have been asked what makes it special for being used in nanotechnology, and the reason is they have uniform size and shape at the nanoscale. So this is the correct answer. Now, uh, okay. So the next question is, virus-like particles, VLPs, differ from infectious virus mainly because obviously, just like I told you. So this is a virion, okay? So this is the viral genome. If you are removing it, okay, then there is no infectious genome here, correct? This is capsid-free virus-like particles. So the correct answer would be B. They lack a viral genome. So they lack a viral genome but keep the capsid structure. Now, the third question was, which plant virus is most commonly used as a template in viral nanotechnology due to its rod-like structure? So you would have also heard about it, and I guess in class 11th or 12th biology book, there is this depiction of the tobacco mosaic virus. So the most common one is this one, the tobacco mosaic virus. Okay, try attempting these two questions. I'll wait for 15 seconds again. Okay, so yes, obviously we can do uh, drug delivery of an, suppose you want to deliver doxorubicin. So doxorubicin has been encapsulated in chitosan based nanoparticles. Doxorubicin has been encapsulated in, silk based nanoparticles, which is silk is considered biocompatible. Even our lab is doing the same thing. So uh, yes, there are different FDA approved drugs like doxorubicin for breast cancer, cisplatin for lung cancer. There are different drugs that has been FDA approved for treating particular cancers, and yes, they are being encapsulated in different delivery vehicles and used for drug delivery. We can do that. Okay, so I'm receiving the answers. Uh, Thank you guys for being so active, for writing answers in the chat box. Okay, so I guess most of you have given the correct answer. Okay, so infrastructure, obviously you need a lab, you need a technical expertise, you need a lab, you need a technical expertise. So that's completely fine. You can do it if you have the necessary raw materials. If you have, like, just like some time ago I told you that suppose it depends what kind of nanoparticles you are making, what you are trying to encapsulate. Suppose, because what happens is, um, if you are able to procure doxorubicin from the market, if you are able to procure cisplatin from the market, and then you have the delivery carrier, basically the molecule, the compound that you are using to make the delivery carrier. But usually these are quite costly. So obviously, in terms of infrastructure, obviously you need some basic instruments like magnetic stirrer, heating block, oven, and extruder, or if you are making it with a quite, some different techniques like silver nanoparticles are there. If you remember in your course content, sir has taught you people about the laser ablation mediated method for synthesis of silver nanoparticles. So for that, what you need a complete setup for that. So obviously, for those things, you need that. But suppose you are not following that laser ablation, yes, obviously, it is, all those setups are very costly. But then, just like I told you, if you want to do only synthesis of gold nanoparticles, or silver nanoparticles, you can buy chemicals which might cost you like 25,000 rupees, and you can, and if you have a magnetic stirrer with heating block, you can make it on your own. But yes, it is costly. Research is costly, so you need a particular setup. You need, you know, all that infrastructure and chemicals and raw materials, and it also depends on for which application you're trying to make it. Which are used in implants for specific drug delivery. Okay, so I would like to know what kind of implants we're talking about. So the question is, does nanoparticles are used in implants for specific drug delivery for cancer treatment? Yes, like for breast cancer, obviously what you can do, if you're just talking about implants, you're talking about implants in what sense? Like, are these nanoparticles? You're talking about nanoparticles or something else? You can write in the chat box as well. But if the question is in generic sense, yes, you can use, you can deliver specific drug at a target site if you are engineering your nanoparticles in that manner. Suppose I'll give you an example. I'll make it clear. I'll give you an example. Suppose there is a breast tumor, okay? There is a patient who has breast tumor, and you know the molecular subtype, that what kind of breast tumor it is. So there are different molecular subtypes, okay? There is triple negative, there is estrogen receptor positive. So based on what kind of which molecular subtype is there, usually there's a combination, but still you do the molecular subtyping to basically select which drugs would be most effective. Suppose it is estrogen receptor positive kind of breast tumor. So you can specifically use uh, drugs that can target estrogen receptor positive type of tumor by encapsulating it in a nanomaterial, and also modifying the surface of that nanomaterial with target moieties that will target receptors present on that estrogen receptor positive breast cancer cells. So yes, you can do it. Definitely, you can do the specific drug delivery for specific type of cancers. So if that was your question, if you still have doubt, you guys are free to write any of your, like, just don't think that okay, this could be a stupid question or like a very simple one. That is completely fine. From extremely simple doubts, whatever basic doubts you have in your mind, just throw in the chat box, and I would be very happy to answer all those questions, because this is for your understanding, this is for developing a base about biomedical nanotechnology. And trust me, this topic is very, very interesting, extremely interesting. Okay. Yes, my obviously I'm studying in IIT Indore, so it is a fully functional lab, uh, and my lab basically is we do nanotechnology based work, we do drug delivery, we do that functionalization, we synthesize a lot of different nanomaterials, nanoparticles. Okay, so the question was, one key application of viral nanoparticles in medicine is obviously controlled drug and gene delivery. So a lot of you answered correctly. Yes, is nanotechnology currently being used for cancer treatment? Okay, so a lot of places for a lot of cancers, yes, it is being used. Now I'll also be very honest. Now, if you see the past few decades, like if we see like past 2 to 3 decades. Okay, so I'll answer one by one. So the first question is nanotechnology currently being used for cancer treatment? So a lot of studies have been approved for clinical trial. The clinical for the clinical trials, and there are some which are already available in the market. Like gold nanoparticles are currently being used, but the major roadblock to nanotechnology to becoming uh, to be used in a full-fledged manner is uh, the basically the resource availability, the infrastructure development that a country can offer. So low and middle income countries like India obviously is a developing economy, and I am very hopeful that in the coming years, that in the coming decades, obviously there would be nanotechnologies. Like nanotechnology is already stepped in for the cosmetics, nanotechnology is already stepped in a variety of places. But to be entirely used for the cancer treatment, there still are certain roadblocks that needs to be addressed. Now I'll tell you one major roadblock to that. One major roadblock to that is, you know, a lot of materials that are used for the delivery of those drugs are in most cases not very cytocompatible. Like one example is carbon nanotubes. So if you are modifying the surface, if you are uh, coating it with some material, then it is fine. But carbon nanotubes alone, after a certain concentration, it becomes toxic to the cells. So a major roadblock to nanotechnology is the cytocompatibility. What does cytocompatibility means? That that particular material is compatible with the cells in our body. So this is one issue. Then the other roadblock to nanotechnology is we are a lot of not very specialized infrastructure wise, and and there is not, a lot of technicality, technical expertise that is available. But still, the research is going in a full-fledged manner. A lot of nanoparticles are already approved, and then I hope in the, I mean, not hope, obviously, in the coming years, obviously, there would be more clinical translation of the nanotherapeutic based approaches for treatment of different cancer. Now, the next question was, okay, so can we use a lab for our experiment? So actually, you'll have to reach out, like there's an official channel. So every institute, every research institute has a proper official channel. So you can reach out to the department, maybe to the PI. Like suppose if you want to do internship, obviously you can do the internship, and during the internship you can do that. Or if you're already working somewhere, if you have interest, if you want to do some of the experiments, because we have a lot of instruments here, like for all the characterizing, for synthesizing the nanoparticles and all those things. For that, you can reach out to the professors who are here and tell your idea, tell your project, and if they'll be interested, obviously they'll reply back to you. So these are the two approaches you can, but you have to follow the official route, because obviously this is a government institution. Then graphene and certain liposomes are being tested out as nanoscale drug carriers, and also now nanobots is also quite interesting and upcoming. Correct. So that's what I told. Nanotechnology is extremely interesting, and trust me when I say this, in the next 2 or 3 decades, there would be, you know, uh, lot of applications that would revolve around nanotechnology. Nanotechnology is the future, and we just, scientists are continuously trying to address the limitations, the shortcomings associated with nanotechnology, and we are quite hopeful that we'll be able to do that. Because, see, like if I tell you about my work, I have synthesized a nanotherapeutic for basically photothermal therapy, correct? Now, I have done the in vitro studies, I have checked its cytocompatibility, I've checked its effectiveness in killing cancer cells. Now, the next step for me would be to check its efficacy on mice model. Once I get, it shows efficacy in the mice model, I can go for the clinical translation. So, this is the usual route. Now, in this usual route, a lot of times what happens is, suppose your the nanoparticle, basically the nanotherapeutic that you have made, showed effectiveness at the cellular level. Suppose in vitro studies you did, and it showed like, okay, the cancer cells are coming, are killing. Now, when you move to the mice, okay, you develop tumor in a mice and you tried treating that tumor with that nanotherapeutic, but it might be possible that the mice, there would be no tumor reduction. So, a lot of studies halt at that point, it fails at that point. So, then you do some modification, again make it more effective. So, this is the usual flow. This is how it is done. And can we get the Okay, so basically you can, like I told you, you can search biosciences and biomedical engineering department, Indian Institute of Technology. Or if you have something in mind, you can also email, maybe you can also email me. I'll drop my email ID. If you have certain doubt, you can reach out to me there as well if you like want to know what instruments or what facilities we have in the lab. Okay, so the next question was cowpea mosaic virus nanoparticles are often explored for. Okay, I'll just drop in here only. Okay, so this is my email ID. So maybe if you have some serious questions, you can definitely drop an email. But a humble request to not spam the email. And but you are most welcome to ask genuine questions, your genuine queries, and whatever comes genuinely out of curiosity. Okay, so Okay, so the question was cowpea mosaic virus nanoparticles are often explored for. The correct answer was solar cell fabrication and cancer immunotherapy. So this application, like, okay, we know it, the virus-like particles, we are loading drug and it can be used for cancer therapy. But how solar cell fabrication? Why cowpea mosaic virus can be used for solar cell fabrication? So CPMB surface can be functionalized to nucleate semi-conducting or metallic nanoparticles. तो suppose ये CPM, this is CPMV. ये जो इसका surface है, this surface, it can be functionalized to nucleate. मतलब you can synthesize basically to nucleate semiconducting or metallic nanoparticles. These nanoparticles are critical light harvesting and electron transport materials in dye sensitized or quantum dot solar cells. So do remember that cowpea mosaic virus nanoparticles are often explored for solar cell fabrication also in addition to the cancer therapy. Yeah, I'm coming to that. I'm coming to that. What are the different methods that are available uh, that are there to develop the nanoparticles? Although sir would have discussed those things. So I have that in the slide. So let us start with, okay, so after this, maybe I can skip, but let's just go in a pattern, question by question, because I've also just, uh, I'm not skipping it because I have complete like physical methods. What are the different physical methods? There are chemical methods and the biosynthesis of nanoparticles. I have included those slides as well. So in the subsequent slides, we'll be discussing that. Now, let us look at this question. Which of the following is not related to Stern layer? Now, if you look at this question and you don't have much understanding of the, you know, nanoparticle in suspension. Now, what is happening? Suppose there is a solvent in which your nanoparticles are suspended. Okay. Now, when your nanoparticles are in suspension state, okay, there would be some surface characteristics of your nanoparticle, correct? So there is a formation of a hydration layer, kind of hydration layer you can call it, or basically electrical double layer that forms around your nanoparticles. So this stern layer basically is a part of electrical double layer. So इसमें पूछा है, in this question it is asked which of the following is not related to stern layer. So stern layer is not actually electrical double layer. It is a part of electrical double layer. So what is stern layer? Stern layer basically is a rigid layer of ions tightly bound to the particle, and ions bound to the stern layer travel with the particle and it is a slipping plane. Now you might not be able to clearly visualize what I am talking about. So that is why I have added an let me explain you what does this mean. Okay. Okay. So suppose this is a solution. Fine. So as you can see, all the whatever particles would be there, it would be less than 1 nanometer. So it is a clear solution. Now, what is a colloid? What forms a colloid? When in a suspension there are a particle which ranges in size from 1 nanometer to 1 micrometer. What is 1 micrometer? It is basically 1,000 nanometers. So whenever the particle size is in the nanometers range, basically it constitutes colloids. What is a suspension? When the particle size is greater than 1 micrometer, we call it a suspension. So suppose these are the three types. Now, when a colloidal particle is dispersed in a liquid, its surface usually acquires a charge. Fine. Whenever a colloidal particle is dispersed in a liquid, इस ये एक charge acquire करेगा. Suppose negative charge acquire करता है. Okay. By ionization or adsorption of ions which might be present here. Yes, definitely. So that is that question that Tanya has asked, that whether it is possible that nanoparticle in suspension form aggregates. Definitely, if that is why there are approaches in which you do capping. Okay, so suppose we are making gold nanoparticles. Okay, suppose we are making gold nanoparticles, and for making gold nanoparticles, there is a method that we call as Turkevich method. In that, we use sodium citrate. So, what does citrate do? Citrate, that sodium citrate acts as a mild reducing agent, but in addition to that, it also acts as a capping agent. So, it will form a kind of cap which will prevent the aggregation of nanoparticles. So, there are different approaches that you can use to prevent the nanoparticle aggregation, and it is very important that your nanoparticles are not aggregating, because then also it will maintain obviously the main property is a larger surface area, it will be able to interact, and that is how the integrity would be preserved. So the goal is to prevent aggregation. Okay. So now coming to the concept, let us understand the concept. So when you are dissolving this colloidal particles in a liquid, its surface acquires a charge. Okay, it is acquiring a charge because of the adsorption of ions or by ionization. Anything could be there. Now to balance this charge, oppositely charged ions. Suppose it has acquired negative charge, so positive ions would come and surround this. Okay. Oppositely charged ions from the liquid accumulate near the particle surface. This forms the electrical double layer consisting of stern layer. Stern layer is the one that is immediately followed by the particle, which is tightly bound counter ions directly attached to the particle surface. And then that, suppose this is stern layer, and it will be followed by a diffuse layer. Okay. So stern layer is the tightly bound layer which shares boundary with the particle surface, and diffuse layer, which is the outer layer, it is a loosely bound counter ions mixed with some co-ions, gradually decreasing in concentration with distance. So this is the concept of formation of electrical double layer. Under what conditions this electrical double layer is formed? And this electrical double layer basically can be visualized as two parts. One is the rigid stern layer and the other one is diffuse layer. So the previous question was based on this particular concept. Okay. So there could be other questions also in your exams, maybe based on this concept. So that is why when I'm discussing any question, I'm also attaching the theory behind that question, from where it came out. Now, I have again added another picture in which I have shown, suppose just like I suppose the surface charge of this nanoparticle was negative. Now there was counter ions of different charge, positive charge that forms a rigid layer, which we are calling as stern layer. And this stern layer is followed by a diffuse layer. So I hope if you guys have watched the videos that were uploaded on NPTEL website, so you would have seen this term zeta potential. Okay, the zeta potential value. So zeta potential value basically measures the charge here. So and it is characteristic. Like suppose different nanoparticles and different zeta potential values are under different solvent. Like uh, colloidal stability means whether particles in a dispersion stay uniformly distributed or aggregate. So it is very important to have a clear idea of the colloidal stability, whether the nanoparticles that you are making are stable or not, or they are not clumping together. So controlled by the balance between repulsive electrostatic forces and attractive van der Waals forces. So a general guideline is, suppose if you are getting a zeta potential value of greater than 30 millivolt, it could be negative, like it could be minus 30 or plus 30. Okay. So if you are getting a value like more negative than minus 30 or more positive than plus 30, it is considered that your particles are stable. In these conditions, your particles are considered stable, and it is, it highlights that it will not aggregate. Okay, so this is the concept for zeta potential. Suppose, why is it important? Why zeta potential measurements are considered an important step when you are doing the nanoparticle characterization? The reason is, suppose you have synthesized a nanoparticle. Your intended application is you want to use it for cancer treatment. You want to deliver it to the tumor site and treat cancer. Now, before that, you have to check whether your nanoparticles are stable in a suspension medium or not. Because if it will aggregate, it will not do the work properly. So for that, we check the zeta potential values. It gives an idea whether the nanoparticles are stable or not. So that is a very important characterization step. Now, stable suspension would look like this, and unstable suspension would look like this. Okay. So, this minus 30 plus 30, this gives an idea about, you know, the kind of forces that are operating between two different nanoparticles. So, suppose the repulsive forces, what does it mean? Okay. Let us understand. Suppose these are the two particles. Okay. So, the repulsive forces between these two particles are more. That is why they are, uh, well separated from each other. They are not coming together. Now, suppose this repulsive forces comes down. Like suppose it becomes 20, it becomes 15, it becomes 5 millivolt. So when this force will come reduce, these particles, these two different particles will start coming closer to each other and will eventually, what would happen? It would aggregate. It will start forming aggregates. So that is why having an idea about the zeta potential values is very important. So zeta potential measurements are taken at slipping plane. So this is the slipping plane. Slipping plane basically is a hypothetical plane because obviously if you know you cannot visualize that okay there is a glass vial. I have added my nanoparticles. Okay, this stern layer is forming. This diffuse layer is forming. Obviously you cannot visualize that. But this is a kind of hypothetical plane. So your instrument basically measures the potential, basically the charge at this slipping plane reflects the effective charge of a particle experiences in motion, not the full surface charge. Now, nanoparticle characterization methodologies, I'll just repeat what you've already studied because since we were discussing about stern layer was eventually related to zeta potential measurement, and zeta potential measurement is a part of what is a part of nanoparticle characterization methodology. Okay, so apart from zeta potential analysis, there are four very important, uh, I would say, methods that are used for characterizing nanoparticles you have made. So the very first is you need to visualize whether it has been made or not. So first one is scanning electron microscopy. So what happens in scanning electron microscopy? We suppose this is our sample. Suppose there is a glass slide. You cut a piece of glass slide and you casted a drop of your nanoparticle sample on it. ठीक? This is a drop. You dry it. You properly dry it. Okay. So you casted a drop of your nanoparticle suspension on a glass slide. You dried it properly. And once it is dried, there is no moisture content. Then it is placed on the sample stage in scanning electron microscope. Then you shine this sample with this incident electron beam. Okay. So there would be different cases. It could be like like how the electrons are produced and basically what the detector is detecting. So in scanning electron microscopy, a focused electron beam is scanned across the surface of a sample in vacuum. So all this is being done in a vacuum. Okay, all this is being done in a vacuum. So the instrument, if you see, if you search on Google, if you look at the instrument, there's a door. You open the door, you put your samples, you lock it, and then you vent it out. There is a step venting out. So in venting out, what happens is a vacuum will be created. So the next steps of analysis would be done once the vacuum has been created. Okay, so basically, whatever you're analyzing is you see in black and white only because that is how the software is made. So it's not like, but there are options where you can add colors in that because when you suppose you are, that isn't made to detect colors, but you can do the color mapping, you can add colors later as well. But usually in microscopy, like there is bright field microscopy concept, then dark field microscopy, so usually it's there because if you remember, it would look like that only, but then there are different staining methods that we used to do, metaxylin staining, eosin staining, to stain the cells to make it look colored. But usually it's you know it is interacting. There's only what, because the source in case of this microscopes, not this, usually bright field microscopy or the usual microscopes that you have at most of the labs, it is a white light source, okay, that you are using for illumination. So you're using a white light source for illumination, okay. So that is why how that is interacting with your sample. Based on that, a contrast is created in black and white color. So illumination source matters. Now, if you stain it, now suppose this is the sample, not in microscopy, usually we do not stain the samples because it is done in dry state. Your samples needs to be dried, free of moisture. So for this, it is not, we do not detect colors in that, but there are different software and I would say like, yeah, software only that is available by which you can add colors of your choice maybe, but that would be hypothetical. because usually it is in dried state only. In this picture, okay, see, in this picture, this is different. Scanning electron microscopy is different, and transmission electron microscopy is different. These are not nanoparticles actually. As you can see, these are pollen grains. So pollen grains can differ in size, but when we visualize nanoparticles, yes, all the nanoparticles would look similar. I'll show you one of the data, one of the data from my paper. I'll show you in the next slide, and you will see that all the particles would look exactly same. Now coming to the okay, so we focus a focus electron beam is scanned across the surface of a sample in a vacuum. The interactions between the electrons and the sample generate secondary or backscattered electrons, which are detected to produce high resolution image. So, जो भी secondary and backscattered electrons, these ones are detected and used to construct a SEM image. Okay. What happens in transmission electron microscopy? It uses a high energy electron beam that passes through an ultra thin sample. Okay, so यहाँ पे there is secondary or backscattered electrons, but in case of transmission electron microscopy, they are talking about the transmitted beam. Transmitted and scattered electrons are then focused by electromagnetic lenses to form images that reveal the internal ultrastructure of the material at nanometer to sub-angstrom resolution. See, okay, because we are using now an electron beam here. So to avoid basically scattering losses, if there would not be vacuum, there would be, if there is air, there would be a lot of scattering losses. So in order to avoid that, we create vacuum in both cases, both SEM and TEM as well. So that is why vacuum is important. Now, another technique that sir has taught you is DLS. Dynamic light scattering again is very important. So what happens in dynamic light scattering? A suspension of nanoparticle. Okay, so you have a cuvette, you put it in the machine. There is a cuvette holder. This carries your sample. Okay, there is your sample. And then there would be, lasers that would be coming, and you can set it whether it is getting reflected to 90-degree or it is in reflected mode. You can select obviously. So I'm just telling you how is it done. So a suspension of nanoparticle is illuminated with a laser. No, these are not scanning electron microscopy, transmission electron microscopy. These aren't actually, give you a correct idea of a three-dimensional structure. Basically, they just tell you about the surface topography, surface morphology, not a correct. I mean, we cannot use the term correct to view a 3D structure. That is a different thing. Okay, so like we can visualize at like how uh, there are if there are layers or there, but we cannot construct a complete 3D kind of image from that. So for that we need to do the z stacking. Okay, so what exactly z stacking is? Suppose you have a tumor kind of, so suppose small tumor kind of thing. So there is another microscopy that we call as confocal laser scanning microscopy. In that, suppose there is a small nanometer size lab made organoid or lab made spheroid. What are those? So we use cancer cells to make a three-dimensional tumor kind of structure. So those are in nanometer scale, like 300 nanometers or 400 nanometers. So in confocal laser scanning microscopy, we keep that 3D structure, I mean the cell confocal wells that are available, and then we collect section by section images. And then there is an option to merge those section by section images, that is Z-stack imaging. And based on that, we can have a 3D look. Maybe in next class, I can put that one figure from my paper in which I have done the 3D imaging. I can show you guys how it looks like. I have used it for seeing whether how effective my drug is for treating, how effective it has been in killing cancer cells. I have done the staining, I have done all those things. So maybe I can show you guys, you will have a better idea. So based on your question, which was like, is STEM 3D and TEM 2D? No. So they basically tells you about the, morphological characterization kind of thing. Both STEM and TEM are morphological characterization. It will not give you a three-dimensional kind of image to you. will just, okay. So these fluctuations are analyzed to calculate the diffusion coefficient of the particle, which is then related to their hydrodynamic diameter. So we are calculating the hydrodynamic diameter of the nanoparticle. The result provide information on the average particle size. Now let us understand what is polydispersity index. But before that, suppose you did nanoparticle characterization using scanning electron microscopy and you found this size. But when you put, because scanning electron microscopy is done in a dried state. I just now told you that you to take a glass slide, you drop a sample on it, dry it, and then you analyze. But dynamic light scattering is done in a suspension state. Okay. You are putting 1 ml of, suppose you are putting 1 ml of sample, which is carrying your nanoparticles, So that is why there's a difference in the diameter. Suppose this is the diameter for scanning electron microscopy and this is the diameter for hydrodynamic, because obviously just now we studied about the formation of the electrical double layer, this hydration layer. That is why there is a difference. Like it could vary from 20 to 100 nanometer. There could be a difference of the diameter. So that is why whenever you are publishing a scientific, uh, whenever there is a scientific publication, when you are publishing your data, it is always suggested not only to rely on one technique to do your nanoparticle characterization, to characterize your nanoparticles with different techniques so that you have a clear idea. Okay, said, okay, I am getting this size in electron microscopy, and I'm getting, suppose you're getting 50 nanometer size based on your electron microscopy image, and based on your hydrodynamic diameter you're getting 70 nanometers. So like it's fine, but if like even if not 50, if it's 100, there could be reasons. But if you're finding your electron microscopy diameter is 50 nanometer, but hydrodynamic nanometer is 350 nanometers, so that suggests that your nanoparticles are undergoing aggregation in suspension state, which is not good. So that is why different techniques, different characterization techniques are available to, characterize your nanoparticles. Now this is the data. Okay, so this one is interesting. Now look at this. This image, if you look at this image, so this is from my paper only. So that got published recently. You can view it obviously on Google Scholar. So if you look at this particular image, okay, you see that the particles are all aggregated. You cannot visualize them clearly. But in case of this image, you can see the particles. You know, all particles are mostly of similar size. So there are two different terms that are used for nanoparticles. The one is polydispersity and the other one is monodispersity. What does that mean? Polydisperse means the system has particles of many different sizes, shapes. As you can see here, it's all aggregated, broad. And when you do the dynamic light scattering, this is the data from DLS, dynamic light scattering analysis. This is the DLX data, dynamic light scattering analysis. Okay, so those students who are joining now are not like, obviously I'll let you in, because for me it's like even if you're studying like 30 minutes, 35 minutes, you will get to know something. But I would still request all of you to kind of please join a little early. But it's fine, okay. So as you can see, this is the electron microscopy data. Now, similarly, you can see there is a broad distribution. I mean, there are particles of 220 nanometers, there are particles of 300 nanometers, 400 nanometers, 500, 600. Okay, so is my screen visible to everyone? Can you please write in the chat box, is my screen visible? Okay, so maybe you can log out and log in again, and then it will be visible to you. You can do it because I guess it is visible to everyone else. Okay, coming to it. So, but if you move to this image, you can see like there is all the particles are all, you can see the particles are all aggregated. Okay, and the same thing you can visualize in this dynamic light scattering data as well. There is a broad distribution range. Means in your nanopart, suppose this is your nanoparticle suspension. Okay, तो इसमें छोटे से लेके बड़े तक सारे रेंज के पार्टिकल्स हैं, मीन्स ये पॉली डिस्पर्स है. दिस इज नॉट गुड. But if you look at this, it ranges from only 150 to 300 nanometer, means it shows narrow distribution. So if your nanoparticles are good, it will show a narrow distribution range when it comes to their size. And the same is, you know, मतलब कि these two data support each other. This is electron microscopy data, this is dynamic light scattering data. So basically, I'll tell you in brief, like in this paper, we have synthesized nanoparticles and we have checked its aqueous stability in three different water-based solvents. So this one is milky water, this one is DI water, and this one is PBS at pH 7.4. So basically, we hypothesized that since this PBS maintains a kind of buffering, has a mild buffering action, which prevents the nanoparticles integrity, and there are ions which keeps it, compact. So that is why we observed the best image in that, and also these two data supported each other. So that is what I was trying to tell you. Monodisperse means the particles or molecules in a system are nearly the same size or shape. Okay, they are nearly the same. If you look this one, they are nearly the same size and shape, narrow size, and it will show a narrow size distribution. But all these aggregated particles, they will show a broad size distribution in dynamic light scattering. So this is how you study, this is how you interpret, this is how you study the scientific data that is available. So whenever any person is synthesizing nanoparticles, these characterization methodology stays constant. It will remain the same. Like everybody has to do that things. Different all those there are different characterization methods also available, but these are the primary ones. You have to do it. Okay, so there are some sample questions based on dynamic light scattering, your SEM, TEM, and zeta potential. So I would like you to just quickly do it. You can write the answers in chat box as well. I'll wait for 10 more seconds. Okay, so this is the answer. Some of you have given the correct answer, some of you have done mistakes in one question or given the correct answers for rest of the two questions. So dynamic light scattering is primarily used to measure particle size distribution in suspension. I showed you the data, what particle size distribution means. Okay, so DLS is primarily used to measure particle size distribution in suspension. In DLS, okay, so in dynamic light scattering, particle size is determined based on absorption of light, diffusion coefficient from Brownian motion. Always remember that dynamic light scattering depends on this Brownian motion. Okay, so there's a diffusion coefficient that is calculated based on this Brownian motion, and particle size is basically determined based on that. So always remember, whenever there is mention of dynamic light scattering, do remember diffusion coefficient from Brownian motion. Now, a PDI, polydispersity index, I just now explained you what polydispersity means. Polydispersity means your nanoparticle suspension is a mix of nanoparticles of different sizes like 20, 50, 80, 100, 300, 500, 600, which is not good. So usually low polydispersity value. If your polydispersity index is low, it means that your nanoparticles are good, because low polydispersity suggests monodisperse system. That is why the correct answer is monodisperse. So basically, you'll the live recording you'll get on the YouTube, which you guys might have the link, or will be shared to you. I'll upload this live session on YouTube as well. And apart from that, you'll have access to this content, I mean these slides, that I have already uploaded in the Google Drive. So there would be a Google Drive and the link would be shared with you so you can access the content from that Google Drive as well. Now, these are the questions for zeta potential analysis, and I want you guys to do it. So let us do it in 10 seconds only. Just a second. Second. Just a second. I'll just have a look if it is being okay. Okay, so these are the answers. So zeta potential indicates, what does zeta potential indicates? It indicates particle surface charge stability in suspension. Okay, so a lot of you have given correct answer. That is very good. See, they could be difficult questions, but this live session initially for the first two sessions, obviously I would be only giving simple questions which might look simple, but it is very important for you to have a solid base, solid conceptual understanding of these topics. What does all these things mean? The second question was a zeta potential. A zeta potential of minus 35 millivolt usually indicates, what does it indicate? It indicates, see, I told you, correct? Uh, just now I told you that when your zeta potential value is greater than minus 30 millivolt and it is greater than means the particles would be stable. That is why the answer is highly stable colloids. In question 5, it is it should be. No, see, if it is greater than minus C, moderately stable, you will tell in that case if you have been given a range of value. Suppose if it is greater than minus 30 millivolt, the general concept is if it is greater than minus 30 millivolt, then generally it is considered stable. Now, if you are given, like suppose that is minus 35 and the other one is suppose minus 31 and suppose the other one is minus 40. In that case, you will call it as moderately stable. But you have no reference, okay? So if it is greater than minus 30 millivolts, obviously it is a highly stable colloid. So you are not given a reference. If it is greater than minus 30 millivolt, it is considered stable. But if you are given if you are comparing it with some other value, suppose you have two different nanoparticles, you recorded the zeta potential value, then you can say that it in comparison to the other one which has minus 40 millivolt, it is moderately stable. It is in comparison to that, it is I can say less stable than the other two. But there's no reference, so the correct answer would be it would be a highly stable colloid. Then the next question was zeta potential is measured using. So the answer would be electrophoretic light scattering. What is happening? Because same DLS, zeta, more or less, the working principles are same. Now, do this one. This one is for scanning electron microscopy. For those people who are mistakenly writing wrong answers, I would suggest you to go through the video, go through the slide again, and go to read these techniques like I have taught you, but I would suggest you to read these techniques one more time. Just now I explained the scanning electron microscopy, transmission electron microscopy. These basically tells you about the morphology of your nanoparticles, basically the surface topography of your nanoparticles. So obviously, correct. A lot of you are giving correct answers. That's very good of you. So, okay. So the correct answer for the seventh question is obviously SEM detects surface morphology and topography, just like them. The resolution of scanning electron microscopy is generally in the range of nanometer. That is why we are visualizing nanoparticles there. Then, to prevent charging of non-conductive samples in SEM, one often the answer is coats the sample with a thin conductive layer. Now, this one is very important. Okay, so I explained you scanning electron microscopy. I explained you that there is a glass slide in which you do the sample casting. Okay. Now, after sample casting and drying, and before putting it in sample stage, okay, before keeping it on sample stage and creating vacuum, there is a process where we do, let me write properly. Okay. There is a term used which we call it as sputter coating. Okay. Sputter coating. What is sputter? What actually happens in sputter coating? We basically coat this sample with a layer of conductive material. Okay. Now, in what cases this is used? So, a lot of times what happens is, especially in case of biological samples, suppose you're trying to visualize cells in scanning electron microscopy. Suppose there are cells. So obviously these are biological samples usually are not conductive. If you are using gold nanoparticles, you can simply cast and view it in scanning electron microscopy because those are conductive. But for those samples which are not conductive, what you do, uh, you know coat the sample with a thin layer of a conductive material. Usually gold is used, but at some places there are some like carbon, copper, or other materials. But usually, in most of the systems, there is a gold coater that comes with that system. So we do sputter coating. So we keep the samples in a sputter coater, and from here the gold is coated on the sample. Okay, one thing I can do, since I have the system here in my institute, I can attach a video or I can attach a photo how that coating happens. It looks very interesting. So in the next class, I'll add that in one slide. So, but coming to the concept of this, that is, this is the sample. You coat it, you sputter coat it with gold nanoparticles, means you are making the samples conductive, and then you are putting it in instrument. So what it prevents charging of the sample, because if you are not putting it with, sometimes it might happen that because of the electron beam your samples would burn out and they would be charging. You'll not be able to focus your samples and see it properly in the microscope, in scanning electron microscope. So that is why for biological samples or mainly for non-conductive samples, it is always suggested to coat your samples with a thin layer of conductive material. Usually gold sputter coating are used. So always remember that. Now these are the questions for your transmission electron microscopy. Try attempting these. Just 5 more seconds because time is running. Hmm. Okay. So the correct answer for the question number 10 is internal ultrastructure at atomic or nanometer scale. The resolution of transmission electron microscopy can reach. Okay, so one thing, uh, why transmission electronscopy in one aspect where transmission electron microscopy is better than scanning electron microscopy is the resolution. The resolution is much better than scanning electron microscopy. It is less than 1 angstrom, and then STEM samples must be thin, typically less than 100 nanometer to allow electron transmission. So that is why, suppose if your samples are in the range of 100 to 1000 nanometers, okay. So usually you can, in lot of systems, if if the instrument is not very sophisticated, usually you cannot visualize below 200 nanometers in scanning electron microscopy, okay. But suppose if you are making nanoparticles which are less than 100 nanometers, means 50, 20, 60, then for clear picture you can use TEM for better resolution. Okay. So for the correct answer would be, it should be thin, typically 100 nanometer to allow electron transmission. Okay. So another technique which sir has taught you in the lecture is X-ray diffraction. So what happens in X-ray diffraction? X-ray diffraction is a phenomena. Okay. So since I was uh, basically telling you briefly all the nanoparticle characterization methodologies, and by far I have discussed scanning electron microscopy, transmission electron microscopy, dynamic light scattering, zeta potential analysis, and now I'm talking about X-ray diffraction. Okay, so 5 different nanoparticle characterization methodologies I am discussing right now. It is a phenomena in which the atoms of a crystal, by virtue of the uniform spacing, this D, this is the interatomic spacing, by virtue of their uniform spacing, cause an interference pattern of the waves present in an incident beam of X-rays. Okay, now what would be difference? Different materials would have different interatomic spacing, correct? And now when different materials have different interatomic spacing, it would interact differently with the coming beam of X-rays. Suppose the interatomic spacing in this case is this. Sometimes it could be less. So how they would interact with the coming X-ray beams would differ. And that is why there you would observe different X-ray diffraction patterns for different materials, which is characteristic of that material. So that is why we use it, this technique for characterizing that. Now, the atomic plane of the crystal act on the X-rays in the same manner as does a uniformly ruled diffraction grating on a beam of light. So suppose there are X-rays coming in, okay. Now these uh, uh, scattered ones basically would interact, either there would be either constructive interference, they would interact constructively, or there would be destructive interference. Usually this is the same. So a beam of X-rays contacts a crystal with an angle of incidence theta. Okay, it is reflected off the atoms of the crystal with the same angle theta. Okay, the X-rays reflect off atomic planes in the crystals that are a distance d apart. The X-rays reflecting off two different planes must interfere. Now this is the condition. Whenever you are reading about X-ray diffraction and you are asked what is that one important condition for X-ray diffraction, you shall know that X-rays reflecting off two different planes must interfere constructively. Because if there would be destructive interference, there would the diffraction pattern that would be formed, it would be very weak in signal. So there would be no pattern that we can observe. So the X-rays must interfere constructively to form an interference pattern. Otherwise, the X-rays would interfere destructively and form no pattern. So this is the condition. Okay. And then there is Bragg's law and lambda 2d sine theta. So basically, we can go deeper into that. But for understanding the basic of this X-ray diffraction, I don't think all these things are necessary. So I'm just dealing it with superficial so that you know what is this methodology and why is it used for nanoparticle characterization. So that is the main motive for me to discuss this. So similarly, same thing is there. If there would be constructive interference, you can see the diffraction pattern. There is diffracted beam is strong and it can be detected. But if there is destructive interference, means the crest and troughs are interacting with each other. Here, the crest to crest interaction. Hai. I mean, there is obviously you guys would have studied about constructive and destructive interference in your previous classes. So in constructive interference, the diffracted beam is strong, and in this case, it is weak. Now, XRD finds the geometry or shape of a molecule using X-rays. XRD techniques are based on the elastic scattering of X-rays. So this could be also a very good question, objective type question, that it is based on elastic scattering of X-rays and constructive interference to form structures that have long range order. The X-rays get diffracted by a crystal because the wavelength of X-rays is similar to the interatomic spacing of the crystals. That is why theta values जो हम देख रहे थे, that was same. X-ray diffraction is based on constructive interference of monochromatic X-rays and a crystalline sample. These X-rays are generated by a cathode ray tube. I mean, this is the source. A cathode ray tube is used to generate highly ionizing high power X-rays filtered to produce monochromatic radiation. What does monochromatic means? It is composed of a single wavelength, monochromatic radiation, collimated to concentrate and directed towards the sample. So this is the XRD instrumentation, okay? So you keep your samples here. This stage is there, and then this X-ray tubes. This is a rotating kind of analysis. So this it keeps on rotating. It keeps on bombarding high energy X-rays, which are then reflected off from based on the interatomic spacing and the different crystal lattice. It gets reflected off, and then it is detected by the detector. So based on that, theta values are you can predict the theta values, which is different for different samples. Okay, so when a crystal is bombarded with X-rays of a fixed wavelength, so you can see this I mean the X-ray tube which is generating X-rays and bombarding to the sample and the detector, and it keeps on rotating. Okay, so when a crystal is bombarded with X-rays of a fixed wavelength, okay, fixed wavelength, I mentioned monochromatic, it was written monochromatic. Cathode ray tube is used to generate highly ionizing X-rays, and then it is made monochromatic. And at certain incident angle, intense reflected X-rays are produced when the wavelengths of the scattered X-rays interfere constructively. In order for the waves to interfere constructively, the difference in the travel path must be equal to integer multiple. You don't have to understand a lot of it, but still you can read. When this constructive interference occurs, a diffracted beam of X-rays will leave the crystal at an angle equal to that of the incident beam. By measuring the angle 2 theta of each diffraction peak, you calculate d for the corresponding crystal planes, and these d spacing are fingerprints of a material's crystal structure. So this is very important, that these d spacing, the theta values are characteristic for a material. So suppose you are making, there is a material whose diffraction pattern in its isolated state, the diffraction pattern of that particular material. Now you are using that particular material to synthesize some kind of nanoparticle, nano construct, or nanomaterial. So, and there are other elements also in that. Now you want to check whether in the synthesis process you are successfully able to incorporate that material or not. So you will take a reference XRD pattern or XRD spectra, and then compare it with the XRD spectra of that nanomaterial. Okay, and then compare it with the spectra of that known XRD material. And based on the peaks that you will see, you can say that, okay, the peaks are at the same position. So I can say that I have successfully incorporated in that material, in that nano construct or nanomaterial that you have made. Now these are the sample questions. So I would just simply give the answers because I have to like discuss some more important points. So why is XRD important in nanotechnology? Because it identifies crystalline phases and estimate crystal size in nanomaterials. Okay, so the B option is correct. And in this case, if XRD, now this is important. This is a very good question also. If your XRD pattern that you are recording and comparing it with a reference material, it shows a peak shift to lower 2 theta values. Usually the XRD spectra that you will get, you will be given this 2 theta value. You compare the 2 theta value compared to the bulk material. It indicates that there is lattice expansion or strain. This is a good question. Now the other one was nanomaterials properties differ from their same mass of material because both. Now, what is the concept behind this conduction and electron motion? Is that if you see what happens on what are the effects on band structure. So bulk material के केस में क्या होता है? The energy bands are continuous. Do you see this? This is the bulk semiconductor material. The energy bands are continuous. Okay, continuous. The space here is very less. In nanoparticles, when you make nanoparticles, यहाँ पे क्या हो रहा है? There is a huge band gap. Okay, so the energy levels, this energy levels, okay, these energy levels are becoming discrete. So always remember that bulk material have continuous energy bands and your nanomaterials, nanoparticles have discrete energy levels. So this was the concept on which the previous question was based. So effects on band structure, band gap widening. As particle size decreases, the conduction band and valence band separate more. You can see it here. Okay, smaller particles, these smaller particles, stronger confinement and higher band gap. Similarly, this explains why quantum dots of cadmium selenide जो भी हम बनाते हैं, for example, emit different colors depending on their size. Okay, and then electron confinement, because there would be confinement of electrons. That is why there are different energy levels, discrete energy levels. So the previous question was based on this concept. Then the other question was densely packed nanoscale pillar structures kill bacteria by, and the correct answer was piercing the membrane of bacterial cells on contact and tearing bacteria. This is kind of physical means of killing bacteria. How does it work? It basically pierces the membrane of bacterial cells on contact and tears it apart. This again, I explained you that sodium citrate that was being used for synthesis of gold nanoparticles, your gold nanoparticles. So citrate here works both as mild reducing agent and a capping agent. So here it is being asked what is the role of citrate in thiols. So since it acts as a capping agent, since it acts as a capping agent, so once it will cap the nanoparticles, there would be no agglomeration or aggregation of nanoparticles. So it prevents the agglomeration of nanoparticles. So this is how it is being done. This is the citrate capped gold nanoparticles. Okay. So role of citrate in nanoparticle synthesis, जैसा कि I discussed Turkevich method. So citrate has a dual role. Always remember this. This is the chemical mediated synthesis of nanoparticles. So mild reducing agent, citrate functions as a mild reducing agent, and in addition to that, it also acts as a capping or stabilizing agent. Same for thiol. Thiol acts as a capping or stabilizing agent for nanoparticles. Then the other question was how the laser ablation method, basically this laser ablation method. So this is your laser source basically, and the wavelength is 532 nanometer. Means again there is a monochromatic radiation, the laser beam that is being focused, and a convex lens being used. I mean, this is the basic optics. I mean, you would have studied in class 12 also that convex lens is used to converge the laser beam. So materials and setup required for silver nanoparticle synthesis by laser ablation method, and this is the answer. Now coming to this biosynthesis of cadmium sulfide, and this is again biosynthesis of nanomaterials, and this particular uh, microorganism is being used. Now, these are the methods of for synthesis of nanoparticles. There are three different approaches. So I was basically trying to come to this slide before finishing off the live session. So let us discuss it quickly. So there are different physical methods. Electrochemical, ultrasonication. What does ultrasonication means? Ultrasonication mein what you do is, suppose this is an ultrasonicator bath, okay, and it is there is water in it. Now you have a nanoparticles which are like the size is like this. If you remember, you would have studied top-down approach of nanoparticle synthesis. What was happening in top-down approach? Basically, there was a bigger size of nanoparticles, and you were by some means you were converting it in smaller pieces of, I mean, small size of nanoparticles. So same is happening. So ultrasonication, there are ultrasound waves, ripples of ultrasound waves that are generated. There is water in it. And when you put your nanoparticle samples in it, which has bigger nanoparticles, it will send ripples of ultrasound waves, which will break your bigger size nanoparticles to smaller ones. So these are the physical methods, just like, you know, uh, we discussed. Then laser ablation, just now we saw that you're using laser to create, to make nanoparticles. Then irradiation, evaporation, condensation. What are the biological methods? Green synthesis. Okay, you're using plant, fungi, bacteria, algae, yeast, actinomycetes. You are using these materials for synthesizing nanoparticles. Okay, chemical methods. We have already discussed synthesis of gold nanoparticles, then silver nanoparticles. There are different etching, mechanical milling, laser ablations, sputtering. Sputtering, just now we discussed gold sputtering on SEM samples, then thermal decomposition. So broadly, the synthesis of nanoparticles are divided into three categories: physical methods, biological methods, and chemical methods. Now, another very important thing is you can follow two different approaches, either a top-down approach or a bottom-up approach. Basically, in top-down approach, you start with a bulk material and then move forward to small nano-size materials. Bottom-up approach, you have uh, different small size raw materials, basically, which you use to create nanoparticles. So that is like you are, it doesn't like the flow always isn't same. So this is the final destination. So you're starting from different molecules, you are engineering that into particles, you are loading it, and you are finally synthesizing nanoparticles. And here you already have a bulk material and using it to synthesize nanoparticles. Okay, so these are some of the techniques. I'll quickly just go through some of these techniques. In mechanical milling, what is happening? Suppose this is the bulk material, okay, and these are milling balls. So you put your bulk material here, there would be continuous rotation of it, and these bulk material will be converted into small sized nanomaterials of similar sizes. So this is mechanical milling. Then etching, yeah, etching, which could be either chemical etching or dry etching. So what is happening? Just I'll explain it briefly. Suppose this is a silver stabilizer, then there is a FeCl3 alcohol solution, and then you have buffer, silver stabilizer, and all those things. So in this kind of, this is a chemical method. Usually these methods are not suggested because they use harsh chemicals in these, and green synthesis is mostly preferred, which is like for especially for biomedical applications. Now laser ablation I have already told, maybe, but I have attached a slide for you to have a reference. You can read it from here as well. So laser ablation is a versatile method for synthesizing nanomaterials without involving the vaporization of a target material. So suppose this is the target material. Okay, you are shining laser, there is vaporization, and then from this, suppose there's a wire of some copper, and then you are making copper nanoparticles out of this. You are vaporizing, and then there is that vaporization is basically followed by condensation and formation of this nanoparticles. This technique is valuable for producing high purity nanomaterials, including semiconductor quantum dots, carbon nanotubes, and cold shell nanoparticles without the need for chemical precursors. There is no chemical precursor, there is only this target material one. And since there is no chemicals involved, so this is green synthesis because there is only laser. Sputtering, again, that I just told you for like sputtering is a physical vapor deposition technique. So there is vapor which gets deposited on your sample. Similar for scanning electron microscopy. Suppose this is a drop of your sample. There are vapors which then gets deposited completely on your sample and makes a conductive layer which is then used for scanning electron microscopy. So all these are like different methods to produce nanoparticle. And then again, this is electro explosion of wire. Simply, you have copper wire and there is vaporization followed by rapid cooling, which leads to formation of nanoparticles. These are some of the questions. So, which approach is followed in chemical synthesis of nanoparticles? So, in chemical synthesis, usually bottom-up approach is followed because you have, suppose you have silver nitrate then you have a reducing agent. Okay, you are mixing both of them, and then you are finally getting the nanoparticle. So that is why this is a bottom up approach. So usually in chemical synthesis of nanoparticles, a bottom up approach is followed. And then again, this is one interesting model, Lamer model. So you can refer to this one. I have attached a slide of this one as well. That there is an optimum, monomer concentration at which nucleation starts. So what is nucleation? When your nanoparticles start forming. Now, as you move forward, as there are monomers available in the solvent, nanoparticle synthesis would keep on going. Now you have to decide that which size of nanoparticles you want. If you want this size of nanoparticles, you can simply halt the reaction here. If you want here, you can simply halt the reaction here. So those optimization you need to carry out. That for how long you need to do the optimum time, optimum incubation time, and optimum concentration. So these are the factors that basically governs this. Okay, so I told you that I will be discussing about the tunability. Okay, so tunability, what is tunability? The capacity to precisely control and modify material properties by varying synthesis conditions, composition, or external stimuli. Now, all of these are gold nanoparticles. Okay, if you see, all of these are gold nanoparticle suspension in water of different size. When the size is 5 nanometer, it is almost red wine in color. But when the size increases, it becomes 80 nanometer, the size becomes more or less purple. Okay, so that is why I was telling why. Suppose if you are adding 100 microliter of reducing agent, 200, 300, 400, different concentration, and you are adding of reducing agent, then different size of nanoparticles would be formed. And you'll also see difference in their absorption maximum. As the size increases, the absorption maxima shifts. So for 80 nanometer, it would come somewhere around here, but for 5 nanometer, it would come somewhere around here. So that's what I was telling, that a lot of different nanoparticles are there, and by carefully engineering it, by carefully uh, tuning the concentration, time, reducing agent, all those things, you can control the size of the nanoparticles. And not only size, you can also tune the shape. You can make nano rods out of gold, you can make nano shells as well. So not only the size, you can also tune shapes as well. Okay, so then there is biosynthesis of nanoparticles, which is also physical method, chemical method, and then this green chemistry mediated and biosynthesis. So these are all the sources from where, all the natural sources. And if you are getting the extract of these from these sources, these are the chemicals that are present in the extract, which function as either reducing agent or maybe as a capping agent and used for green synthesis. So this is the source precursor. So you are getting silver from here, and these are the reducing agents. So they will basically reduce, and it will make silver nanoparticles. And since you are using these natural sources, biological sources, it is considered green synthesis. Okay, so these are some of the sample questions. Microorganism. So the answer for this one is, biosynthesis of nanoparticle typically uses which of the following as reducing and stabilizing agent? So the answer is microorganisms and plant extracts. Gold nanoparticles have been successfully synthesized using which plant product? Aloe vera extract. So all questions you can basically do it later as well. I have added some questions for your reference, and this was the last question. So basically, this is the last topic that I will be discussing for this live session, and then we can end the session. So atomic force microscopy. I discussed SEM, TEM, DLS, zeta potential, and X-ray diffraction. Another very interesting technique is this atomic force microscopy. Okay, so what this atomic force microscopy is, let us quickly understand. So what is happening in atomic force microscopy is a high resolution microscopy technique used to study surface topography, properties, and interactions. Okay, so AFM works by measuring the internal forces between a sharp probe tip and sample. Suppose this is your sample. Okay, you have casted a sample and it has nanoparticles in it. Now this is the tip and this is the cantilever. You call it a cantilever to which a tip is attached. Now this cantilever moves throughout your sample in a raster scan mode like this. फिर इधर आएगा, then this, and moves it in a raster scanning mode. The probe is mounted on a flexible cantilever. This is a flexible cantilever. Always remember, because this is the essence of this technique, that there is a flexible cantilever. Now what happens is you shine laser on it. While this probe is moving through your nanoparticle surface, this you shine laser on the cantilever surface. Now this probe would interact differently. Suppose it is moving like sometimes there's particles and it will move somewhat like this if there are nanoparticles here. So based on this, this laser, because this is a flexible one, now when it will, have a rough patch or a rough surface, it will bend. While interacting, this probe would bend, and whatever amount it would bend, it will deflect the laser beam. Suppose if it bends, there would be the laser that is reflected off from the cantilever would be here. So based on this data, there is a detector which detects these changes and give atomic force microscopic image. So as the tip scans across the surface, attractive or repulsive forces causes the cantilever to bend or deflect. It causes the cantilever to either bend or deflect. A laser beam is focused on the back of cantilever and reflected into a position sensitive photodiode detector. Okay. The deflection of the cantilever is recorded and converted into a 3D surface image. So yes, since one student was asking, so this one gives you an account of the 3D, you know, just a second. Okay, so 3D kind of structure. So this is atomic force microscopy. There are different types. Like uh, either there's a contact mode where the tip touches surface. Non-contact mode, tip oscillates close to the surface. So basically, laser is shining on this AFM cantilever, which is flexible, and based on the bending, different patterns are obtained. And these are the different modes of AFM. This is basically for your knowledge purpose. Applications, we can see the surface morphology at nanoscale. We can measure mechanical properties. We can image biological samples. So that's it for today's lecture. Maybe the different more applications of nanotechnology we can deal. However, it is like simply common. Just in brief, I'll explain. Uh, you would have heard about brands like Creepy Sanon's hyphen brand. Then there's Minimalist. So a lot of sunscreen advertisements that are currently being done, you would say non-sticky formula, lightweight, water-based formula, non-sticky formula. So what does that actually mean? Those are actually nano emulsions which are used in sunscreen. Okay, so this is a nano emulsion kind of thing. These are nano emulsions, gel solution, which are being homogenized. That is why that no sticky formula. So what are nano emulsions? They are extremely fine. Yes, you can get recording of this session. This all session would be uploaded on YouTube. Like we have been asked to upload it on our YouTube, and then you can from there you can have the recording of this particular session. So you would there are different skincare brands. In the advertisements they highlight these are their USPs. Those sunscreen creams, that lightweight formula, no sticky, no white cast, nothing. So again, there is nanotechnology there. So nanoemulsions are extremely fine oil in water or water in oil mixtures with droplet sizes in the nanometer range, 200 to 200 nanometer. They can encapsulate UV blocking agents. So in those nano droplets, there are different UV blocking agents that are encapsulated. Now, suppose you are now what is the you know advantage of this when you are applying sunscreen on your skin? Okay, now since there would be sustained delivery of this UV blocking agents, so that is why it will last long and protect your skin for a long time. So there will be sustained release of these bioactive molecules which usually blocks UV, like titanium dioxide or zinc oxide, which is loaded in there, and disperse them evenly, which prevents clumping. So this is all nanotechnology. Simple, like sunscreen. A lot of you might be using sunscreen, but you might not have paid attention. Okay, what exactly means when they are saying lightweight, no sticky, no white cast formula. So this is the concept. Okay, now when you're talking about topical diseases such as psoriasis, there are other things as well. Now, whenever there is an open skin wound, usually it is suggested that you know there should, it depends like what kind of I would say manifestations it has on your skin. Sometimes it is you are advised to not cover it up, not to put any uh, you know just kind of thing that would uh, attract basically water there, because of which there could be other infections, bacterial infections and all those things. So if you're talking in general term, like we can, if we can develop some topical kind of application, if we can have. So it depends that what molecules we want. Suppose if there is psoriasis, what exactly we want to target, what are the different bioactive molecules which can actually cure psoriasis. Based on that, we can load those molecules in the nanoparticles and make a gel kind of. There are different, you can read about hydrogel kind of thing. So in that hydrogel you can load those bioactive molecules. Is someone trying to say something? uh, okay, so there are only, then I have given some biomimicry based questions and example like shark skin inspired swimsuits and all those things. You can just solve these sample questions as well, but since the time is complete, so I don't want to take much of your time. Okay.
அப்புறம் தெனுக்கு இங்கே எல்லாம் போயிருமா இங்கே இங்கே எல்லாம் போயிருங்களா
Okay, so is, I don't know where is the sound coming from. Okay. Okay, fine. So that's all for today's lecture. I hope you guys would have developed some insight, have drawn some insight based on these lectures. If you have any, doubts, you can reach out to me. Yours, this one, you will be getting like, you'll get the video uploaded on YouTube, and apart from that, the content also you will get on the Google Drive link that will be shared with you. So thank you very much. It was great having you all, and the best part was, uh, you guys were actively involved. You guys were interacting, and since like for this, with this course, it was my first session. So in the subsequent lectures, I would try to maintain a continuous pace while interacting with you. And thank you very much. Thank you very much.